My name is Beibei Zhang. I'm from the Zhejiang lab. Today I'm going to present our research work, Dynamic DNN Decomposition for Lossless Synergistic Inference. Here is the outline of this presentation. First, I will introduce you the motivation behind this research. Why is this topic important? Next, I will show you some of the related works to demonstrate the past research efforts. Then, I will show you the proposed system of our research and give you a system overview. I will point out two major algorithms, which are HPA and VSM. The experimental results prove the effectiveness of our algorithm. And at last, I'll give you a conclusion and point out some future directions. As we all know, the inference process of a deep neural network requires abundant computation resources and energy. As an example, a smart robotics runs out of battery in 20 hours with accurate vision identification function, and a smartphone lacks powerful GPU to process large CNN module. So, people think about using cloud computing to offload all DNN inference to the cloud. However, the network bandwidth between the devices and the cloud servers is narrow, unstable, and expensive, and it incurs a long transmission delay. Further, we have to transmit all the raw data to the cloud servers. It leaves the privacy concerns to the end user. Recently, we have a new computing paradigm, which is edge computing. We try to partially offload the DNN inference to the edge and the cloud. This is because we observe that the intermediate results of a DNN may be smaller than the raw data in size. But previous research overlooks the end device resources, and they do not fully utilize the edge resources. Here is the related work. We categorize the related works into two groups. The first group is called horizontal partition. In 2017, neurosurgeon partitioned a chain topology DNN to two parts in layer granularity via traversal. The simple traversal tries to find the optimal cutting point of a chain topology DNN. IONN further optimizes the solution via shortest path algorithm. It also tries to partition a chain topology DNN, but it uses auxiliary points to form an auxiliary deck topology and find the shortest path on the deck topology. We can see that DNN becomes more complex recently, and there are more and more deck topology DNN. So DNDS proposed to partition a deck topology DNN to two parts via min-cut algorithm. However, all these three methods only split the model into two partitions. They overlook the computation resources at the end device side. Besides, early access solutions sacrifice the accuracy. And in this research, we only consider the solutions that are lossless. The second group, we call it vertical separation. In 2017, field-style partition slices a stack of correlated feature maps spatially and distributes the stack to a computation node. AOFL further extends the above idea and provides an algorithm to find an optimal partition. However, they do not consider the padding in the convolution operation, and it leaves a precision loss. So, we propose Dynamic DNN Decomposition System, so-called D3. Our system consists of three major components: profiler, offline partition framework, and online execution engine. The profiler collects CPU information, GPU information, and memory. Together with the layer config, it predicts the layer processing time of a DNN with a regression model. Both regression model prediction and the network condition become the input of a horizontal partition algorithm. The HPA algorithm split a DNN into three parts, and the vertical separation module further separates the DNN part assigned on the edge to multiple field-style stacks, and it assigns a fuse-tail stack to a node. The offline partition framework passed the decision to online execution engine, and the online execution engine form a pipeline to process the DNN. Here are the algorithms that are important in our system. The first algorithm is horizontal partition algorithm, which aims to split a DAC topology DNN into 3 parts. And we assign these 3 parts to 3 tiers. Our idea is first to stratify a DAC topology DNN. In this example, you can see that we stratify a DAC topology DNN into 5 layers. According to our proposition 1, we shrink the search space in splitting the DAC topology graph in 3 parts according to multi-weight, multi-edge weight, and multi-vertex weight. We refer to a vertex Vj as the subset input sibling vertex of Vi if Vjp is a subset of Vip. If the optimal tier of Vi cis vertex Vj is before Li optimal, cis updates the optimal tier of the cis vertex to Li optimal. So, cis updates further optimize the processing delay and the transmission latency of a cis vertex. Combine the proposition 1 and the proposition 2, we get our heuristic algorithm, which is called horizontal partition algorithm, shown on the right. The second algorithm, we call it a vertical separation module. It aims to process a CNN layer and a pooling layer where we are separating a sequence of correlated input feature maps to multiple feature map stacks. We can see that there are paddings on an input feature map. So every time if we want to find the corresponding coordination of a feature map in the previous layer, we need to deduct the paddings, which is important and the critical in our algorithm. Our algorithm vertical separation module is shown on the right. Here are the experimental results. First, I will introduce you the settings. The network settings are like this. The edge node and the device node are in the same local area network, both of which connect to the cloud node via the internet. And I show the average uplink rate between 2 nodes in this table. The device settings are like this. The device size is a Raspberry Pi 4B with 4 GB of RAM. And on the edge side, we have multiple Linux machines with Intel Core i7 8700 CPU and 8 GB of memory. On the cloud side, we have a remote server with NVIDIA GPU and 256 GB of RAM. Here are the experimental results. I show the HPA-only performance in these 2 charts. The first chart shows the end-to-end latency speed up among HPA, device-only, edge-only, and cloud-only under different network conditions. The second one compares the HPA with the state-of-the-art. And this chart shows the latency speed up when we apply both HPA and VSM. And the device and the edge connects to the cloud via the Wi-Fi. So we can see that HPA accelerates the end-to-end latency up to 28.2 times compared with the device-only approaches. And it outperforms the neurosurgeon up to 2.33 times. It outperforms DADS up to 2.97 times. Combined HPA and VSM together, it surpasses the state-of-the-art up to 3 times respectively. So, in this research, we introduced a system called D3. It consists of HPA and VSM. HPA partitions the DNN module into 3 parts according to the per-layer processing time and interlayer transmission delay. VSM further divides the feature maps of a DNN layer assigned to the edge node into multiple fuse-tail stacks for parallel processing. In the future, we can use Ray to ease the implementation of the D3 system. Here is the reference list. Thank you.